did a thesis with Scott Tremaine. I notice it has a lot of citations, that thesis, on Kozai cycles and tidal effects and shrinking of orbits. That stood you in good stead later on, talking about exoplanets. And then he came here as a Michelson Fellow, Prize Fellow, that morphed into Sagan Fellows later, and did a Hubble Fellow at Santa Cruz, and then landed back at Chicago as an associate professor now. So he was here from 2007 to 2010, and Kepler launched on March 6, 2009. So he was here for those exciting times when we were discovering things that none of us had thought of to put into the concept study report in the science section. Maybe one or two sentences about multiple transiting systems, but man, we were so excited about multiple transiting systems of planets in compact coplanar configurations, and you could use the transit time variations to do dynamical stuff. And then the circumbinary planets, short period planets, many of them eclipsing, with circumbinary planets around eclipsing binaries, and fairly large planets, and kind of at the edge of stability. And other things, but those are the two you're going to talk about today, I think, so I better let you get going.
Okay, thanks. Okay, wonderful to be here. So yeah, we're talking today about resonant chains and circumbinary orbits. And the work has been done over lots of different papers with lots of different collaborators, and I'm highlighting students who've come to UChicago and worked with me on some of these projects. Also, here's a senior thesis student from Peking University, who was I'll show some of his results at the end. Okay, so the big picture in exoplanets is very data-driven. The theorists kind of get to go along for the ride sometimes, as I had a great time with Kepler. But you see a multitude of ideas for how to find exoplanets, and a notional sensitivity of each of these ideas as you decrease the mass that these different methods are sensitive to. The first ones, first rocky bodies around stars were around pulsars and got down to ridiculously low masses. But then we followed the photometric line down the transits, down ground for, well, Dave Charbonneau is right here, and followed that path for the first time. And then we went to space this is basically the reason I came to CFA in 2007, because I knew Kepler was going to launch, and I knew a lot of you all were right in important contributors and originators of that mission. So following that track has gotten down well below Earth mass, close into the star. And these numbers, of course, are extremely out of date because it's 2013. So then another path opened up with transit timing variations. On top of that, space-based photometry, following down a dynamical path, similar to radial velocity, but just one branch over. TTVs has discovered a few planets and characterized their orbits at above super-Earth masses. But it has also, of the ones that are transiting, which you'll see today, it's pushed way, way further down, where we can characterize the planets that we know to be there through the transit method. So I'll put the upper limit on the date 2013 for the original Kepler mission, which, of course, it was resurrected as K2, continuing observations beyond 2013, but these were the heyday in which a 4-year data set was assembled, which is extremely important for the long baseline timing, which I'll show today. We are talking, of course, about how to extend this to TESS. TESS has year-long dwells at the poles, so we can find a lot of similar results from TESS, but what we experienced in just that first year of Kepler data. So today I'm not talking about the great follow-up opportunities that we do have now with TESS, but that we could say that for the question, somehow how some of these ideas will be enabled to go in different directions with RV follow-up. Okay, so although they may look like they're worshiping this golden idol, no, it's a scientific endeavor, and it has produced scientific plots. Okay, you're going to see plots. So the planet radius versus orbital period plot is displayed here from a student that came. Becky Dawson made this plot. She was a student here, and I got to work the summer before she started graduate school with her, and we published some cool papers together. That was a great pleasure. So she made this plot based on Kepler discoveries as of 2014. There is an update coming up of this plot very soon in a paper that Jack Lissauer is leading called Architectures 3. So that will be maybe the final word on Kepler multiple planet transiting systems. But as of 2014, we had planet systems up to 6 planets and 7 planets transiting individual stars. And so here they are, showing you how many planets transit the star associated with each of the planets. And so you have the 7-planet system, Kepler 90, here with gas giants in the outer parts and rocky planets probably in close to the star. And what we see, which is very clear, is that the hot Jupiters, those original transiting bodies, in around 3 days and 1 Jupiter radius, they are quite lonely. They do not have companions nearby. It turns out they do often have companions, but on very hierarchical orbits, those planets might in fact be responsible for creating the hot Jupiters, but there aren't, these planets haven't come along in on a disk with the hot Jupiters. So it's looking that hot Jupiters, although they inspired some early papers on the migration story, that planets, gas giants can form at 5 AU and then slide into their star on a spiral in orbit. Hot Jupiters inspired that story in the mid-90s, but I think they're not the best evidence of it anymore. And so the two kinds of architectures I'm talking about today form the new best laboratories for migration in a gas disk. In particular, when multiple planets, so let's take a 4-planet system, there's 4 planets in this blob that have formed and gotten very close to the star, just 10 days. And so the question is, can we find evidence for them piling up? Can we find evidence for them spiraling in based on the orbital architectures? What's more, planets are extremely common. About half of stars host a system of planets, and the small ones are especially common near the star. And this is a result recently through spectroscopic analysis, doing a better job at figuring out the radius of the star. This diagram is cleaned up and shows 2 different humps. A hump that is associated with 2.4 Earth radii, which is smaller than the 4 Earth radii of Neptune, and a hump that's below about 1.4 Earth radii. So this has commonly been understood as super Earth planets, a little bit more massive than the Earth down here, that do not have a massive atmosphere, and ones that have a massive atmosphere, much more massive than the Earth, but nothing like Neptune. So this bump is around 1 to 2% in their mass is hydrogen and helium gas. So these are called subneptunes, and these are super Earths. So we'll come back to that theme, what we can do with those. I would be remiss not to show a plot that's made me famous, which is the Kepler orrery. This is a plot that shows, as a function of time, the positions of all the multiple planet systems. This is now a little long in the tooth as well, 2013. And you could see the 7 planets of Kepler 90 here. An 8th planet was added by Chalou and Vandenberg the Google planets, we like to call them, because they used validation algorithms from Google. This is Kepler 11, which is the first system where transit timing was used to find the masses. And in this plot, I ordered them by size of the outer orbit so that we can zoom in and see the highest frequency ones buzzing around. So you can get seasick with this, so be careful. So a great diversity of systems to work with, and a great diversity of period ratios to plot up, because the transit method gives us very precise orbital periods, and therefore we can divide two orbital periods in multiple planet systems. This is a scheme I cooked up for spreading out the period ratios in such a way that we can see several different features that aren't obvious in other kinds of plots. So one of the features is that there's a hump around 2 to 3 days. It's a very broad hump in the period ratio. That is very similar to the solar system. You have the Titius-Bode law that gives us a period ratio of about this. But when we look out in exoplanet systems, it's much broader. There's hierarchical ones where there's a planet in close, like in Kepler 10, and then a much more distant planet. Some of these could have intermediate planets between the known transiting planets. Another feature that besides the hierarchical ones, this stretch also allows us to look in close at these resonances. I've labeled the first order resonances along the top here, 2 to 1, 3 to 2, 4 to 3, etc. And all of those are associated with a peak in this distribution. These first order resonances where it's n plus 1 to n, those are the resonances that matter the most when you have circular orbits of planets that are spiraling into the star, held circular by the disk, dissipation in the disk. Yet nevertheless, the first order resonances can capture planets into them. This was recognized long ago with GJ876 around the turn of the millennium, that pairs of planets can trap into resonances. And now we have some extremely great examples of these resonances. The best one is Kepler 223 in the following sense. It's the periods between individual pairs are right on, within a part in 1,000, right on top of the resonance. So we have, in this system of 4 planets, a 4 to 3 resonance connecting the inner 2, then a 3 to 2 resonance, the next 2, and a 4 to 3, the next 2. So this is also fantastic because if you have a 3 to 2 next to a 4 to 3, then the inner and outer of that triplet talk together with a 2 to 1 resonance. So you can put this together as a 8 to 6 to 4 to 3 resonance. So this was similar to the Galilean satellites where you have a 4 to 2 to 1 resonance. This is a system where all the planets are interacting with one another. So this general architecture seemed to be unique until we did a little more analysis with Kepler 80 and eventually Trappist 1, seeing that although they are separated from the exact resonances by a fair amount, there are other subtler clues that I'll talk about today, that there really is a dynamical resonance among all the planets. The Google planets also included an additional planet in Kepler 80, not shown here. Okay, so this may be a one-off system or a three-off system, but I think it's actually a lot broader than that. There are a number of other systems, Kepler 60 from the original set, like Kepler 223, and then Jesse Christensen et al. Found with K2 a system of 5 planets, all of them in 3 to 2 resonances. So each pair is separated by 3 to 2. So that's a fantastically rich system as well. Previously, I had suggested that HR8799 might be in resonance, although that's yet to be perfectly proven. And again, GJ876 started this game with a 2 to 1, 30 to 60 day periods back in 2001, and then a third planet was added to that chain So I'm trying to show you that there are 4,000 planets out there, or planet candidates, believable planet candidates, a lot of them coming from Kepler. And most of them are in this broad period distribution where we don't see resonances. On the other hand, there are a good handful, even more than a handful, of systems where not only are there resonances between individual planets, pairs of planets, but there's a whole chain of planets, just as one would expect from migration. So let's go a little deeper into Kepler 223, my favorite. So what you can see here is the transit timing variation diagram. This is a very difficult system to analyze. I'll show you in the next slide a little bit. But we have 4 planets, and the data are binned up to see their transit signatures here. These timing diagrams for each of the planets show you if it's a positive number, that the planet is arriving late onto the star, and if it's a negative number, it's coming early. So this is timing variations on the order of an hour. The outer 2 planets of this 8 to 6 to 4 to 3 resonance have several hour timing variations, and they're very clearly anti-correlated. This one swoops up then down, and this one down then up. This was not an easy system to analyze. Usually the protocol is to assume a constant shape model and slide it along the data to determine where the mid-time is for each of these light curves. For this system, the planets are small enough and the noise is high enough that we needed to abandon that approach, and instead, on a quarter-to-quarter basis, so this is 90 days, 90 days, 90 days, take the data and phase it up at the different orbital periods of the planets. So you can see that Kepler 223d, the third planet out, has a nice strong signal. The blue is just empirical binning of the black points. So it has a nice strong signal. And then that signal gets a little earlier here in the last panel. And then the outer one has a clear signal every quarter, and then it gets a little later. So that is the timing signature that you see in this plot, this anti-correlation, this hook in the last couple of quarters. All right, so we have just a data plot over here. So these are planets B, C, D, and E. And then here's the photodynamic model. So this is a technique, instead of having a shape model that you slide through the data, you just compute an n-body model. Work out from positions of the planets in your model what the photometric effect would be, and then match point for point the data to this n-body model. So for those 4 planets, we see the n-body model here, and you see the hook that I was talking about occurring in both of these planets. What's more, in these kinds of systems, if there's a resonance, it could be that planets overlap, their transits overlap, and they do so repeatedly because of the resonance. And so that's what you see, this other transit coming through, kind of messing up the data. Well, this kind of model can easily handle that. It's just put it in the n-body cooker and work out what the data should look like. So this was a heroic work led by Sean Mills, my first grad student at U Chicago. And it used photodynamics to fit the data, Monte Carlo technique to find all the errors. And then finally, that wasn't enough. The data themselves are consistent with too many random orbits. You could get this hook from a very eccentric planet that torques the other guy. So what we also needed to supplement this analysis with was long-term stability. So this constraint put us in a very clear part of parameter space. And here's the answer. We have, at the dynamical epoch, we have orbital periods, and then we can write down the masses in Earth masses and the radii in Earth radii. So the other thing is, from the resonances, we expect sizable eccentricities to be excited, and that's in fact what's seen. These eccentricities, though much smaller than you often see in gas giant systems, they're pretty large for super Earth and Neptune systems, we found out. So the upshot of this is that we have radii that are similar to Neptune, which is our 15 Earth mass planet in our solar system, but the masses are half or less than Neptune's. So these are in the sub-Neptune class. The age of the star is 6 gig-years, so we know that it has to be very stable in order to have survived this long. All right, so transit timing fits give us the masses and orbital eccentricities. So now we can concoct a story, flesh it out a little bit now that we know the masses and the planet types. To get that much gas to make a sub-Neptune, you need the planets to have formed in a gas disk. So let's put some planets in a gas disk and see how they interact. So this is a simulation of the period ratios and orbital distances as a function of time. And when they reach resonant locations, they excite each other's eccentricity. That's the jostling here. And they stick in those resonances. So the three lines here are the orbital distance, the semi-major axis, the apastron, and the periastron. So the orbital eccentricities that you saw in that previous table are well explained by capturing into these resonances. And then the system can just find a quasi-steady state where it spirals in towards the star to the currently observed orbits. So we can't necessarily put a limit on how far it came in from. In other words, it could have started pretty close to it where it existed and only moved maybe 20% in radius. McDonald and Dawson have made that point as well. But nevertheless, this kind of resonant chain is consistent with having formed far out and migrated in. The context of forming and spiraling in on a gas disk informs us that they should indeed be first-order resonances, and we can revisit that when we come to Trappist 1. All right, Kepler 80 is the next one that Mariah McDonald worked on. And this is a system of, at the time, it was a 4-planet chain with a non-resonant planet inside. So the innermost planet is a 1-day planet. The next one is a 3-day planet, so that's rather hierarchical and doesn't speak to each other through a resonance. But then you have 3 more planets exterior to it, and they're all near resonances, near a 3-2, near another 3-2, and near a 4-3. What's amazing is that the period of transit timing variations that you get from the offset from resonance, because in a resonance they can torque each other and change each other's orbits. If they're shifted slightly off the resonance like this, then all they feel is a periodic perturbation from the resonance. And you can write down with this form the period of that perturbation. And it turns out that all 3 of these cases fall at 192 days. So there's something going on that's controlling the whole system and telling the spreads exactly how far to spread away from resonance. That was recognized as early as 2011 that there was a suspicious thing going on. But what it took was further analysis to understand that why they all conspire that way. So what's going on is a 3-body resonance. It's a relationship between the orbital longitudes of those 3 planets. There's 2 pairs of 3 planets here that are in the resonance. So this angle is composed only of lambdas, meaning it doesn't depend on the orbital eccentricities of the planets. But they can capture into a dynamical situation where this angle librates. It sticks around a certain value. And then that itself ensures that the TTV periods all have to be offset by the same amount. All right. Also, what's more is that these angles, if you neglect the eccentricity, if the eccentricities are rather small, like 1%, then you can write down the lambdas in terms of observables, the time of a transit and the orbital period. So this means a quarter of the way around the orbit past the time it passes the sky plane, it comes to transit. So then you have 90 degrees at transit, and then modulated by just the integers after that. So we can plug that into here and get an observational version of the three-body angles. So that's just transit times of the three planets, the periods of the planets, and then we have a certain degree. So then we can check one versus other, the theories of capture into a chain of resonance against the observations. So this one, this kind of equilibrium that a chain of bodies gets into was really explored well by Delis. He did it for Kepler 223, and he found that the observations put you in this little box here of remember, 4-planet system. It's like there's 2 back-to-back 3-body resonances. So then you can write down phi 1 and phi 2 for the inner 3 planets and the outer 3 planets of the 4-planet chain. So Delis found 6 different potential equilibria for this system of 4 planets, and here they are. And it's just probabilistic which of the equilibrium the chain falls into. There's a lot of Hamiltonian math to it, but what you can spy in these different equations are 3-to-2 resonances between the pairs, but also crucially, this is not right on 180 and 90. It's off of it. That's due to the cross terms between planets 2 and 4 and between 3 and 1. So those 2-to-1 resonances, this term gives you the 2-to-1 resonance between those 2 planets. They matter for determining the theoretical equilibria. Okay, so to drive that home, the non-adjacent resonances, these 2-to-1s between non-adjacent planets, gives you an equilibrium different from 0 and 180 degrees. Okay, so the match is very good for Kepler 223. How about Kepler 80? So now we turn to orbital mechanical n-body simulations with damping in order to put the 4 planets of Kepler 80 into resonance, and then I'll spread them back out to the observed ratios. So this is the period ratios at 1.5. So they probably migrated into those individual resonances, captured in the 3-body resonance, and then moved back out. So what do I invoke to move them back out? Well, it's pretty simple. When they get to these deep into the chain, like we see for Kepler 223, their eccentricities are pretty excited between 0.02 and 0.05. Put that system too close to the star, and tides will be raised on the individual planets, which causes their eccentricities to get pushed down. The resonance is such that there's a relationship between how close you are to the resonance and how high the eccentricity gets excited by the resonance, the forced eccentricity. And so as a function of time, as the eccentricities get pushed down, the period ratios lengthen and push you right out to the observed ratio. So what I've done here is a simulation with a pretty extreme eccentricity damping, so non-physical. This is not what tides would do. A time scale of damping of 10 to the 5 days on the innermost planet. And then the innermost planet of the chain communicates that damping to all the other planets, pushing them away from the resonances. All right, so it naturally approaches the observed period ratios of all the pairs of planets all at the same time. It also predicted what the libration angle is. So remember, Delis told us that there is a Hamiltonian formalism that predicts a series of potential equilibria. Well, this numerical model fell right into the equilibria that are actually observed. So these so-called Laplace angles, just like in Galilean satellites, Laplace realized that there was this relationship between the phase angles of the moons. These Laplace angles in exoplanets are exactly where they were predicted by the n-body model. So this modeling effort also predicts small amplitude libration. In other words, the damping causes these librations to damp out so that they are, as observed, they're only a few degrees. So now let's turn to TRAPPIST-1, the gorilla. So I say that because it has 7 planets. They're spread between 1.5 and 18.7. And if you write down their period ratios, you notice that they're pretty close to the resonances too. But again, spread out from the individual integer ratios. So we can do the same thing that you just saw in Kepler 80, which is write down the transit timing variation frequency, the offset from the resonance that is caused by these non-integer period ratios. And you make this chart and you see a lot of repeated numbers, minus 0.002 cycles per day. And so if you invert that, you get 490 days. This is the time scale in which the orbital periods are oscillating in Kepler, in TRAPPIST-1. The other thing you notice is that there's 2 non-first order resonances. The innermost pair is 8 to 5. The next 2 are 5 to 3. So that's kind of a head scratcher. Didn't really see that one coming. How does that come from a spiral? And so one thing you also notice is that these TTV frequencies are nominally a factor of 2 and 3 higher. Well, that just works out due to the 3-body resonances. If you combine pairs of 2-body resonances to make a 3-body resonance, then you have to get twice the frequency near the 2 second-order resonances and 3 times the frequency near the third-order resonances. So what I'm saying from this chart is that all of these planets are one system talking to one another on a long time scale through their mutual perturbations. The TTV data set has been used to find extremely nice masses by Grimm et al. For these planets. It's leveraging a little bit off of K2 data, but a lot of investment with Spitzer. The K2 data revealed the outer planets period. In fact, this logic about the phase angles told us what the period should be for this outer triplet to be librating. So this is a table that shows you the P's and Q's of these 3-body resonances and what angles are sampled in the data. So this is kind of like a libration center and an amplitude moving between these different angles. So let me give you that a little bit more physically. This is a video of TRAPPIST-1, all 7 planets, and then we'll focus on just the outer 3 planets. What it means for this angle to be 180 degrees is that when 2 of the planets cross one another, the 3rd planet is on the far side of the star. There's something similar going on in the Galilean satellites where they're 90 degrees off when 2 pass each other. So that configuration just keeps on repeating due to this 3-body resonance librating near 180 degrees. So, of course, it's a good equilibrium to find if you want this system to remain stable for billions of years, which it has. But it's also indicative of eccentricity damping, which has found this minimum in energy space. So if you liked my 8 to 6 to 4 to 3 numbering that we had for Kepler 223, you will like even more TRAPPIST-1, which is like a clock with 7 hands. Talk about an orrery. So if you crunch the numbers, I hope I did this right. I got down to 24 to 15 to 9 to 6 to 4 to 3 to 2. Quite a dramatic realization of a whole system. So the analogy breaks down a bit here where I pretend like, anyway. It's a pretty fantastic system. And the upshot is that migration plus damping, tidal damping, can have the same effect in this system where we have here the 7 planets start near their observed periods, but then I put some migration on the outer planets, and that causes them to capture one by one into resonances. When these resonances get captured, the planets excite their eccentricities above about 0.01, but then tidal damping pulls down the eccentricities, pushes the planets back out to the observed ratios. So here's, just like the previous plot for Kepler 80, here's the observed ratios of the periods, and then the system just slides right out to that observed ratio all at the same time. So this is a concept that Tamayo noticed also, that the period ratios can all sync up in this fashion, that the three-body resonances hold all the observed ratios as they should be. So what we have over here is that the numerical model also predicts the correct Laplace angles, which were reported by Luger et al. So you have a horizontal line in black, and the data points are matching the observed three-body angles. So remember that these things are damped. Even though the period ratios get pushed away from the resonance, we have damped librations. How much damping? Well, we need some damping coefficients to quantify that. And I said I put in a non-physical number for how much eccentricity damping is. Well, you could scale that up to the whole length of the system. So here in this simulation, it runs for 300 times 10 to the 3 years. Okay, that's nothing compared to the age of the system. But we can scale that up so that we get the period ratios observed today and find what tidal Q value is needed for tidal damping on the inner planets in order to push the planets out to their observed values. So for context, Earth has a tidal Q of 40, Mars a little bit less than 1,000. So that's what we have for terrestrial type planets. And then we get up to about 1 million for Saturn and Jupiter. It depends on exactly what constraints you use, but that's the scale. So this differentiates terrestrial planets from gas giants. So the name of the game is to start the chains at the nominal resonance location where they should have migrated to, and then spread them for the age of the system. And that gives us a lower limit on Q, because if Q is smaller, that means more dissipation by tides, and the chain would have spread further by now. Whereas it gives you an upper limit on Q because there needs to be enough damping for these three-body librations to have damped down to small values. All right, so we can look at the three systems I talked about and place them on mass radius space, and also look at where their planets live in this sub-Neptune super-Earth space. I can select the planets for which tidal damping should be the most important. They live here, here, and here. So this is like a sub-Earth planet, a super-Earth planet, and a sub-Neptune planet, which is likely giving the strongest dissipation for each of these systems. So then I can convert these planet names into tidal damping coefficients, and we have values that are consistent with terrestrial planets in the sub-Earth and the super-Earth, and then just a lower limit on this one because it hasn't spread away from the resonance. This is Kepler 223. And this is starting to be inconsistent with a rocky body, but more consistent with a sub-Neptune type body. All right, so to wrap up this part, we have planetary masses and eccentricities from transit timing variations, resonant libration properties that give us constraints on migration. If there was turbulence in the disk, it could break these resonances. So to see them at all means that they have not experienced too much drama in the early days of the system. And then we have tidal dissipation of these different kinds of planets that causes them to spread away from the resonance and gives us a new handle on what their physical nature is inside. So we can come back to this table if you want to know all the details. But I want to go on to planets around binary stars. So this was the first one where it's transiting a pair of an eclipsing binary. It was called Kepler 16. It was done in large part so Lawrence Doyle was the first author. He had a long-term interest in finding these kinds of systems. Josh Carter who is in Cambridge here, and at the CFA did the work of photodynamics. My role was kind of looking at qualitative behavior, but also the eclipse timing variations that gave us the mass of this planet. To skip to the summary plot of what has been discovered so far, this is slightly out of date, but it gives you the idea. We have about 10 systems of planets, and they exist. What I'm showing here is the orbit of the binary, the primary and secondary, and then the planet orbiting around them. In a lot of cases, the binary is rather circular. This is a small mass ratio binary, so the secondary has a much larger orbit. Here's a nearly equal mass binary on an eccentric orbit with a moderately eccentric companion. All right, so what was found was that these planets often exist about as close as they can to the inner binary without going unstable. For a given mass ratio and orbital eccentricity for the binary, one can set up, Matt Holman started this long ago, can set up test particles around such a binary and tell you where the test particles start going unstable. So that defines a instability zone against which we can scale all the inner orbits of these planets, these blue planets. So here's the instability zone graphically and where the planets live. It's about tens of % outside the instability zone, typically. There are a few planets now known several times the instability zone, but this is clear evidence of pile-up, that they come right to the edge but don't go over, which was actually predicted. Theorists who were working on migration, particularly Nelson, so he did simulations in a gas disk around a circumbinary, around a binary star, and watched the migration of the planet. And they were good at stopping just before falling in. So the understanding of this was developed a little bit after the observation in simulations was seen before the observation in the real world. But then the understanding came after some more detailed discoveries. So here's a nice way to show it. So this is the orbital radius around a binary star. It's for the Kepler 16 binary. Low mass ratio, rather low eccentricity. And so what you're seeing is the surface density of a disk as a function of radius, and how a planet interacts with that disk. In certain scale heights and viscosities of the disk, a planet can carve a nice gap. So in this red one, it's carved a gap and sits there. In other cases, the planet can get pushed all the way into the inner edge just right next to the binary star. So there's a peak in the surface density of the disk due to the binary star the egg beater effect. It's throwing out the mass near the binary star, launching waves into the disk, and that holds the disk at bay. So here's another couple of authors worked on it, where they showed the scouring in surface density of the inner parts of the disk. So when a planet migrates in on such a disk, it can get hung up at this location because it sees a flow of mass near itself that no longer pushes it in in the co-orbital region. So we expect this kind of thing to happen when the planet's low enough mass not to totally disrupt the disk. The disk has to stay pretty much coherent and controlled by the binary. If that's the case, then the planet can respond to the disk. This is true for Saturn mass planets, whereas Jupiter mass planets, their resonances fall strongly in the disk, and just their resonant effect on the disk continues to push the planet in towards the stars. So Jupiter mass planets are bad at stopping just outside the instability zone. So this really gives us some handle on the physics of interaction between the planet and the gas disk when the planet is migrating. All right, so they've gone to town, tried to match different planets. Here's Kepler 16, 34, and 35. In general, it's not that easy. And they can often not get all the way down to the observed orbits. Here's the semi-major axis of Kepler 34, here's 35. So sometimes the planets are stalling too far away from the instability zone, according to the disk physics that's put into these simulations. So this is an opportunity. It's telling us that we don't know everything about the observations yet. More disk physics can probably be learned by modeling these in more detail. Okay, so this is rather coplanar. I forgot to mention over here, in all of these cases, this is the edge-on, or the face-on view that we would imagine, but the edge-on view is like this. This is what Kepler actually sees. Eclipsing binary with a very coplanar additional planet. The least coplanar of the observations so far is Kepler 413, which has only a 4-degree mutual inclination between the binary and the planet. So this also speaks to planet formation in a disk, that the disk will fall into the plane of the binary and be warped into that plane if it doesn't start out that way. And then the planet will form in that disk and follow suit. On the other hand, there's a new idea, which is, well, it's not that new. Farrago and Laskar foresaw it in 2009, where they said, okay, so this is a Hamiltonian approach to the problem. Where is the secular equilibrium of a disk around a binary? And what they found was not only aligned orbits, but also 90-degree circumpolar orbits can exist. In fact, there was an observation of an ALMA disk just this year where Grant Kennedy saw a eccentric binary, and then over the poles of the binary, perpendicular to the long axis of the binary, is where the disk plane lives. So this actually came up at lunch. Ramesh, you said that, well, the Milky Way must be very prolate to get the kind of cylindrical orbits that has been seen with Gaia. So this is, in fact, the same kind of thing. You have a inner potential, which is prolate, and then in the limit of eccentricity 1, these guys are going to look like just a long stick, a barbell or maybe a needle. And around that needle, who cares if you're in the plane of the binary? It's better to be in this plane perpendicular to the needle. So that's the way to understand this equilibrium. The question is whether we can distinguish coplanar planets with circumpolar planets with eclipse timing variations. And so this is Jean-Bo Zhang's paper about to be submitted. We used Kepler 34 as a test case because we know that it's coplanar. We also see eclipse timing variations of the primary star over the secondary and the secondary star over the primary. And it's only at the level of 1 minute. But the model matches the data very nicely for the coplanar case. But for a circumpolar case, if you tune things to match the primary eclipse timing variations, you just get the wrong phase of the secondary variations. So this is something that you would notice in just 1 or 2 orbital periods of the planet, that the phase of the primary and the secondary need to be right to give you a coplanar conclusion. So it's true for this case with its particular eccentricity and omega, and Jean-Bo did a suite of orbital eccentricities of the binary and omegas to our line of sight, and saw that the amplitude ratio between primary and secondary eclipse timing variations and the phase shift between primary and secondary variations depends on whether you're coplanar in this column or polar in this column. So it seems like a general tool that we can now use to distinguish these two architectures. All right, so to wrap up this part, we have found with Kepler about a dozen planets around eclipsing binaries. They are all very nearly coplanar, just slight perturbations from that. And the conclusion is that formation followed by migration is preferred because we can understand some of the properties of these planets based on this model. And the details of that planet-disk interaction, as in the case of resonant chains, the details are important. So this is setting up quite a long modeling effort that will go for years to come. So I'll take questions. Thank you.
Open for questions. Earl, count on Earl.
I don't have a very important question, but I was curious. In the beginning, you showed this plot of resonances versus number of objects in them, and there was a dip right near 3 to 1.
You're 3 to 1.
2 to 1.
3 to 1.
Let's look.
Sorry? Yeah, right.
So up here it's,
There's a peak
this is
to
a
the
3 to 1.
left,
Yeah.
and I was wondering if you had any comment.
Okay. I think it's just Poisson statistics because this is the total number here, and this is 30. So square root of 30 is 5 to 6, and so then the height of this is just over 5 or 6. So it's easy to be to latch on to these
some
peaks.
of the other peaks.
Now,
and say,
there's a whole publication, Stefan and Wang, analyzing this peak at 2.17. That's a complete mystery. They tried to do the statistical analysis, and I checked it. I don't have any killer criticisms of. They say this is significant, and I don't understand that it's anything but that. So it looks significant, and no one has an idea of where that comes from. But yeah, I wouldn't put stock in some of these other peaks and valleys. There is a significant dip here near 2 to 1, and that has led to some sleepless nights. But I think it can generally be thought of as a carving out from close and interior to the 2 to 1 resonance to pushing planets just exterior to the 2 to 1 resonance by some of the same, like by tidal damping, like I showed today.
Hey, Dan.
Hi.
I have a question for you about Trappist 1.
Yes.
And if you've calculated how much tidal heating there is and whether that could affect any atmosphere that might be outgassed over time and what the timescales are.
Yes, I have calculated it, but I think it's, even in the early days, it's pretty negligible because the star is an M dwarf and it was very luminous in the pre-mean sequence. This would have done a much better job at desiccating the planets than any further the tidal effect.
Too bad.
Yeah. Oh, the other thing to notice, which I didn't emphasize in this, it's kind of funny with Trappist 1, because of the 8 to 5 resonance. Can you find it? Let's go here. The 8 to 5 resonance does not force a very large forced eccentricity. These first order resonances do have non-zero eccentricity associated with them. So tidal damping causes these two planets, because they're not in first order resonance with anyone, they go to very small eccentricity. And you saw that, you see that here. The inner two planets go down to about 10 to the minus 3, whereas the other planets, even today, are forced to of order 10 to the minus 2. So those two inner planets of Trappist 1 are not necessarily causing the spreading. I attribute it to that little guy D, who's the third guy out here and has about 6 times 10 to the minus 3 eccentricity and is getting the brunt of the tidal damping. Of course, it depends on exactly if all of the planets have the same Q or not, who dominates the damping. There was a nice paper by Papalouzeau who showed that the inner two planets have a forced eccentricity, but it's due to, even though they're pretty far from the 3 to 2 resonance and the 4 to 3 resonance, or let's see, I guess they're both pretty far from the 3 to 2 resonance, but nevertheless, that's the resonance that forces them to this 10 to the minus 3 value. So anyway, these are really ridiculously small eccentricities to think about when we're accustomed to the 0.5 eccentricities of gas giants, but that's where we've gotten in this kind of study.
Joey?
Great talk. When I'm listening to all this, a lot of the timescales that you're referring to are quite long, and so the immediate question, kind of that you hinted towards in the beginning, was what is TESS going to do for both, the circumbinary planets and also this kind of dynamical work as well?
Okay, so clearly the reason to do TESS is that you can do radial velocity follow-up, right, Dave?
And then atmospheres.
Yes. Okay. So on the architectures, the radial velocities will tell us much broader picture of what planets are there, because transits have a 1/A bias, so that tends to push you right towards the star and find all the very close planets. And in fact, that also tends to bias you towards small period ratios. RVs are very gentle dependence, a to the minus 1/2. So that dependence, the K amplitude depending like that, allows you to find much more distant planets. And I think what we can do is then have just a broader view of systems where there's inner planets, like we've seen from Kepler, and then detect gas giants out there accompanying these planets. So whereas I showed this plot where most of the planets in multiple planet systems were sub-Neptunes and super-Earths, I think that can change with TESS, because you can detect those giant planets out at a couple AU. And then you have the photons to do it as well from the host stars. So that's the main thing I'm looking forward to. So that also means that since it's not biased towards small period ratios, I don't expect TESS to find a lot of resonant chains necessarily. If it does find them, we'll need to do some massive follow-up work to get transit timing variations. So that's will be very hard.
So we're 4 months into TESS,
Yeah.
data posted. 5 and 6 months are going to be coming soon. Isn't it about time we found something as exciting and different as we were finding in the first half year with Kepler?
I don't know anything, but maybe you do. Are you saying get back to work? Well,
He's looking very happy.
You keep telling us about tidal damping.
Yeah.
Is that a catch-all phrase for heating of the atmosphere or the planet interior or whatever, and dissipating orbital energy into basically heating?
right. Okay, so in giant planets, we have a multitude of theories and very little certain understanding about how the energy goes from orbits into heat. But yes, it is. The end members are orbital energy on the one hand, mainly working on the eccentricity to circularize as the planet circularizes, it moves to slightly smaller semi-major axis. That releases orbital energy, which goes into heat in the envelope or in the mantle of the planet. For the Earth, it's dominated by its oceans. So,
Okay, one
yeah.
more question.
I have a question about those super duper periods. Is it a pure game of numbers, or does it mean that there is some body that you don't detect, like a massive planet on a slightly tilted orbit that you don't see as a transiting planet?
Right. So I've claimed that I can understand these angles. These are the observed angles, neglecting the eccentricity component. And I can understand those with a numerical simulation having just these 7 planets. It's a good question, is how sensitive those predictions, here that's not the right slide, this is the right slide, with those 3 body angles matching between theory and observation. So this was a bit cherry picked. I had to run about 10 simulations for every one that I found matching all the right numbers. And that's just the same idea from Dali, that the theory would predict a bunch of equilibria, and then nature would select one. So the question is, if you had an 8th planet in Trappist 1, would you be able to see it based on not getting the equilibrium right? That's quite possible. You'd need a pretty massive other planet, and according to the DeLee paper, it seems like you would need that planet to be simultaneously in resonance with 2 other planets, like a 3-to-2, 4-to-3 set, in order to affect the equilibrium of the next 3-body chain over there. So it's a fun game to play. I mean, we could add that to the methods of detecting exoplanets, but it hasn't borne fruit yet. The closest it's come is in that Google planet, Kepler 80, that another planet was found in the chain. So it was done with Trappist 1. The period of H was correctly predicted based on the 3-body chain. It was seen in transit, just one transit, and then its period guessed at based on this logic. Guessed correctly. And then that was also done for Kepler 80. So it's a good way to guide you to know where to look for a transiting planet. But it hasn't completely predicted a planet from scratch yet.
Well, thank you again for a wonderful talk.
Oh,